Okay, let's think about this invisible world around us for a second. All these radio frequencies, right? Powering our phones, our cars, even satellites way up there.
It's everywhere, isn't it? A huge invisible network.
Totally. And it's built on basic stuff like capacitors. I read somewhere we make over 4 trillion a year, mostly using nickel.
Yeah, trillions. Nickel is standard for most.
But you sent over something interesting about a special kind, RF capacitors.
Right?
Designed just for these, like, high-speed signals.
Exactly. Your standard capacitor, it's great for, everyday electronics, but when you get into radio frequencies,
They hit a wall.
pretty much, they start to struggle. And that's where these RF capacitors are absolutely critical.
Okay, so that's our mission today then. Let's really get into what makes these RF capacitors different, why they're so important for all this high-frequency tech.
Sounds good.
Okay, so we know what RF is, why we want higher frequencies despite the challenges.
Yeah.
Now, bring it back to the capacitors. Where do these special RF ones actually get used? Give us some examples.
Oh, they're basically everywhere that high-frequency signals are involved. Think about RF power amplifiers.
The things that boost signals for broadcast.
Yeah, broadcasting, any kind of wireless communication, they're essential there. Then you've got cellular base stations, 4G, and definitely 5G networks.
Okay.
Wireless LAN, so your Wi-Fi routers at home or the office. The big telecommunication networks carrying calls and data, GPS systems.
GPS, too.
Yep. Even the keyless entry system for your car, Bluetooth uses them. And they're getting huge in cars now, V2X communication.
Vehicle to everything for safety and self-driving.
Right, that stuff. Plus the car's own powertrain electronics, the internal communication systems. It's kind of amazing how many places they pop up.
Wow, that really is a wide range. Okay, so they're fundamental. Now let's get into the nitty-gritty. What makes an RF capacitor special? What are the key things that set it apart from, those trillions of standard nickel ones?
Okay, there are really 4 main characteristics you need to focus on for RF capacitors operating at high frequencies.
4 keys. Got it. What's number 1?
Number 1, and maybe the most important, is very low equivalent series resistance, ESR, especially at those high frequencies.
ESR. Okay, break that down. Equivalent series resistance. What is that and why low?
So ESR is basically the capacitor's internal resistance. It's not perfect, right? There are small losses in the dielectric material.
The insulator bit.
Exactly, the insulating layer. And also losses in the electrodes, the metal parts making contact. Now, the problem with any resistance is when current flows, it creates heat.
Heat. The enemy of electronics.
Pretty much. The higher the ESR, the more electrical energy gets wasted as heat. And in RF circuits, you often have significant power flowing, and it's oscillating incredibly fast. So even a small ESR can lead to a lot of heat.
Which is bad because...
Well, it lowers efficiency, wastes battery power. But worse, it can actually damage the capacitor itself or other components nearby. Things overheat, performance degrades, stuff fails. So, for RF PAPs, minimizing that ESR is priority number 1. Less heat, more efficiency, better reliability.
Makes total sense. Okay, so how do they get the ESR so low? Is it different materials? Different design?
It's really both, a smart combination. On the material side, for the dielectric, they almost always use what are called Class 1 ceramics. C0G or MPO are the common types.
C0G NPO.
Okay.
Why those?
Because they inherently have extremely low electrical losses. They're just very efficient insulators at these frequencies.
Right.
But maybe even more critical is the electrode material. And this is the big difference from standard capacitors. Remember the nickel?
Yeah, the standard workhorse.
For RF, especially cost-effective ones called BME, base metal electrode types, they ditch the nickel. They use copper instead for the internal electrodes.
Copper. Why copper?
The resource you shared had that great comparison, figure 2, right? Showing the resistance of nickel wire versus copper wire as frequency goes up.
Yes, that was really clear. The nickel resistance just shot up after, 10 megahertz?
Yeah.
While the copper stayed pretty flat.
Exactly. That huge spike in nickel's resistance, that's largely due to something called the skin effect and other weird high-frequency loss mechanisms. Copper just performs much, much better up there. Its resistance stays way lower.
So copper electrodes are key for keeping ESR down at RF frequencies.
Absolutely fundamental for BME RF capacitors. It's a core design choice.
Okay, low ESR is king. What's the second key characteristic? You mentioned quality factor, Q.
Yes, quality factor, or Q. It's basically a measure of the capacitor's efficiency. Think of it as the ratio of energy it stores versus the energy it loses or dissipates.
The energy lost is heat due to ESR.
Precisely. A really high Q means the capacitor is great at storing energy and wastes very little as heat. Low loss.
And how does Q relate to ESR?
They're inversely related. Lower ESR directly means higher Q. Ah, okay. They go together.
Exactly. Since RF capacitors are built from the ground up to have incredibly low ESR, they naturally end up having a very high Q. You'll often even hear them just called high Q capacitors because of this. It implies low capacitance usually, but critically, that's super low ESR.
Got it. Low ESR, high Q, bro Q, both about minimizing energy loss, minimizing heat, especially at high frequencies. Makes sense. What's number 3?
The third one is capacitance stability versus temperature.
Okay, stability. Why is that so important?
Well, think about tuning circuits. Like in an old radio, you turn the dial, you're adjusting capacitance to tune it to a station. Or impedance matching circuits in, say, an amplifier or antenna system.
Right, making sure signals flow smoothly.
Exactly. In those kinds of applications, you need the capacitance value to be very precise and stable. If the capacitor's value changes just because the temperature goes up or down,
The tuning goes off, or the impedance match fails.
you got it. The circuit drifts, performance tanks, maybe the whole thing stops working correctly. So RF capacitors need to hold their value steady, even if it gets hot or cold.
Precisely. And again, it comes back to those class 1 dielectric materials, the C0GNPO stuff. They are specifically chosen because their capacitance changes very, very little over a wide temperature range.
Stable performers.
Extremely stable. Figure 3 in that resource showed it really well. You see the line is almost flat across different temperatures. That kind of reliability is just essential for RF circuits to work consistently.
Okay, stability is crucial. That leaves one more. The series resonant frequency, or SRF.
Yeah.
This sounds a bit more complex.
It is a little more nuanced, yeah. So no real-world capacitor is perfect, right? Besides resistance, ESR, it also has a tiny bit of inductance built in, just from its physical structure. We call this equivalent series inductance, or ESL.
Okay, a little bit of inductance.
Yeah, unavoidable. Now, as the frequency of the signal going through the capacitor increases, the effect of this tiny inductance, its impedance, also increases.
Makes sense.
The series resonant frequency, SRF, is the specific frequency where the capacitive nature of the component and this unwanted inductive nature effectively cancel each other out. Its impedance is at a minimum right there.
Okay, cancel out.
Yeah. Below the SRF, the component acts like a capacitor, which is what you want. But above the SRF, that inductance starts to dominate, and the component starts behaving more like an inductor.
Ah, so it stops being a good capacitor above that frequency.
Exactly. It loses its desired characteristic. Think of like pushing a swing. It has a natural frequency where it works best. Push too fast or too slow, it gets awkward. Same idea. The SRF is the point where the capacitor's own inductance starts messing things up. Figure 4 in the material showed that impedance dip at SRF pretty clearly.
Okay, so above SRF, it's not acting like a capacitor anymore. Why is knowing the SRF critical then?
Because for many, many RF applications, especially those pushing into really high frequencies, you must operate well below the capacitor's SRF.
You need headroom.
Lots of headroom, ideally. If your operating frequency gets too close to, or worse, goes above the SRF, your circuit just won't work as designed. The capacitor isn't doing its job.
So RF capacitors need a high SRF to give you more room to operate.
Exactly. They need to be designed specifically to push that SRF point as high up in frequency as possible. That means careful physical design to minimize that inherent inductance, the ESL.
This is incredibly helpful. Low ESR, high Q, stable over temperature, and a high SRF. Those are the keys.